Oh, I think I just, 1 second, I made a small typo. I just realized that, sorry. All right. Share screen again.
Rose, while you're presenting, will you be able to see us? Do you prefer us having our videos on, or what is your preference?
I can see you guys. You guys can decide whether you want to keep your videos on or not.
Okay, I think most of us are here. Shall we start? Hi everyone. We're very honored to invite Professor Rose Yu today here to the UCL NLP talk. Professor Rose Yu is an associate professor at the University of California, San Diego. She earned her PhD in computer science at USC in 2017. She was also a postdoc at Caltech. Her research focuses on advancing machine learning techniques for large-scale spatial temporal data analysis with application to sustainability, health, and physical sciences. So let's welcome Rose to our today's talk. And everyone,
Thank you.
if you're okay or comfortable, please turn on your computer screen so that, yeah, we can have a better discussion, right?
Okay, sounds good. Well, thanks a lot for the invitation. I want to share some of the recent work from our group towards this ultimate goal of building an AI health scientist. So, and I have this word foundation model in the title because that's what everybody talks about today, right? And so there's a lot of success in foundation models. For task in image, text, image, image to video, text to video, text to image. So I guess what changes in terms of paradigm for foundation model is before we would have to build a different model for each of those tasks. So when it comes to like spatial temporal modeling, that means we need to build models for forecasting, for causal discovery, for scenario creation, for surrogate modeling. But the promise of foundation model is now we just need a single model that can do all these tasks, right? And that's kind of shown in this benchmark on the right from Stanford AI report says like, okay, if you look at the performance of each of these benchmarks, a lot of them focus on language modeling and computer vision tasks. They're getting much better than before. Some of them even surpassing human performances, especially those PhD level science questions. So besides the existence kind of question alone for scientists, we might need to ask, like, do foundation models really solve all our problems? So there is this paper published like a while ago now in the time scale of machine learning, right? And they pointed out some of these easy problems that LLMs can get wrong. Because of the speed of those LLM models development, I don't think these examples hold anymore for today's frontier models, but I still think it's useful to take a look at what type of mistakes these models make. For example, if you ask which weighs more, a pound of water or 3 pounds of air, the model will say something like 2 pounds of brick will weigh more than 3 pounds of air, right? Or you ask spatial reasoning questions, say if you get out of top floor at the street level, how many stories is the building above the ground? Note that you're already on the top floor at the street level, but the model will still say that the building will have a total of 3 stories above the ground. So these simple mistakes that LLM makes just highlight the fact that these models still don't have a pretty good framework of spatial and physical reasoning. So that's the focus of our group, which is try to bridge this gap of physical reasoning with data-driven machine learning models. We have actually dabbled into like NLP only recently. So our prior experiences in physics-guided deep learning is mostly focused on spatial temporal time series data, which has a lot of physical knowledge embedded in how the data is generated, right? As we know, deep learning are purely data-driven model. They're very expressive. They can also leverage high-end GPUs to do efficient computation. But then because they're black box models, they don't have a framework of physical reasoning. They're also very hard to explain how the predictions are made. And of course, we need to have huge amount of data to train these models that's suffering from high sample complexity. For spatial temporal data, however, a lot of times these data are generated from certain physical systems. So we have a lot of knowledge about how the underlying differential equations are and what are the symmetries in the systems and so on and so forth. But these models, however, are very expensive to simulate at high resolution. And then they also have very poor computational budget. So you can see there's complementary strengths between these two families of approaches to model massive amount of data. Right. So the idea of physics-guided deep learning is trying to combine these two things together towards trustworthy AI and science. So we wrote a survey paper published last year at PNAS together with my student, trying to categorize different type of techniques in this area with a special focus on learning dynamical systems. Specifically, we characterize techniques from where you have a lot of inductive biases from physics to where you only have very weak knowledge about underlying system. So you have techniques like residual modeling or trainable operator learning to disentangle representation. Just to give some examples of the effect or the impact of this type of framework, right? And I can just show you some applications really quickly. For example, we worked with CDC to model the progression of pandemic diseases, right? So in this case, you would have these physics-based simulators that described how people's mobility would change the transmission of a disease, and you will need to run Monte Carlo samples to understand the transition dynamics. Unfortunately, this type of simulation is very expensive. Typically, take about a week to run 100 scenarios. By scenario, I mean different parameters like, the disease virus characteristics, the school lockdown policy, and different travel patterns from users, right? These, typically will correspond to one scenario. We built deep learning surrogate models that combine physics simulation with observational data. Well, guess what's special about this deep learning surrogate model is instead of pre-generating all the data beforehand, we have a Bayesian active learning strategy to iteratively update the model and query the simulator. So in this way, you can see as we train the model interactively with the simulator, we can save a lot of the training data needed to learn this surrogate, right? So this deep learning model, once trained, it can mimic the behavior of numerical simulators, but much faster. So as you can see, the truth is the output from the physics-based simulator, and the predictions is from our deep learning surrogate model. This is a probabilistic deep learning model, so therefore can generate confidence intervals over the next a month, right? So as you can see, the mean prediction matches the ground truth quite well, but also the confidence intervals. And what's more important is the speed. So we can accelerate the simulation time from 1 week to now 1 hour. We also participated in the CDC national forecast during the COVID-19 era, and we were ranked #1 among 40 also national teams for forecasting COVID-19 uncertainty. A completely different application is in climate modeling. So there you have very similar problems. You have these physics-based simulators. They're extremely expensive to run. Instead of 1 week, these models actually take about 6 months to do one model run. And so there's a lot of interest in the climate modeling community to build digital twins or surrogate models for these climate simulations. Obviously, we thought about using diffusion model as a generative model to mimic the behavior of physics-based simulations, but regular diffusion model will be too slow to sample for high-dimensional videos like this. So instead, we have this dynamics-informed diffusion model that can couple the dynamics of underlying system with the dynamics of the diffusion modeling sampling process itself, therefore significantly speed up the sampling procedure of diffusion model. So the left is the sample from the physics-based climate model, and then the middle and right ones are the samples from our model called spherical diffusion. So this is a specialized diffusion model with spherical neural Fourier operator at the backbone, and we were able to shorten the simulation time from what used to be 6 months now to 1 week. This model actually can generate very stable rollouts for global climate at 6-hour resolution for 100 years. Compared to some of the baselines over existing emulators developed by Allen 2 Institute, we actually got 7% improvement. So this paper got the best paper award at ICML Machine Learning for Earth System Modeling workshop. Another example is in the field of drug design. So in this case, we wanted to generate new compounds for targeting various disease. And then you can build a generative model to suggest the new molecules. But the challenge there is you have to make sure these molecules are chemically valid. And also you need to measure the properties of the molecules in terms of binding affinity, right? So binding affinity is essentially a physics-based metric to quantify how well a molecule will bind to the particular protein target with molecular forces. And calculating this kind of property is very expensive, as you can imagine, because we need to simulate the movement of atom level motions, dynamics for both the protein target and then the ligand, which is a small molecule. So in this generative model, we actually integrated these physics-based simulators with a generative model that therefore we can guide the generation with the signals from the physics-based simulator. So then this compared to reinforcement learning-based search method, you can shorten the speed of the runtime by significant. And what's interesting is that this model can actually generate high quality ligands that bind well with human, say in this case, human estrogen receptor that has even better binding scores than some of the drugs on the market. So we are actually working with experimentalists to test some of these compounds in the lab. We also coupled some of the simulators with different levels of fidelity. So we have a recent paper at ICML talking about a generative model that interacted with a variety of simulators, from very cheap simulator like molecular docking to very expensive simulator based on molecular dynamics based on binding free energy calculation. And then the generative model will use Bayesian active learning to select which simulator to query and improve its generation. So as you can see, a lot of the examples is around this idea of AI co-scientists. We want to build tools to accelerate and the discovery for scientists, whether they're in public health or climate science or chemistry and drug design. But we're tackling it from more like a numerical simulation and kind of dynamic modeling perspective. Recently, however, there's a lot of interest from the commercial world to develop AI co-scientists. You probably heard this idea of an open AI. I don't know why the video is not playing. That's okay. And then we have Google has this AI co-scientist idea to automatically generate new ideas for you and search for relevant papers. There's also this new platform from Anthropics called Cloud for Life Science, where you can actually just ask a cloud to suggest to you what type of experiments that there might be you can run and what are the relevant literatures that you can do. So I think these companies are tackling this problem of AI co-scientists leveraging the power of large language model. And that got me to think like, okay, we have been building AI co-scientists more from numerical simulator side using physics. Can we actually combine the power of large language model with our numerical based simulation guidance, right? So that's the idea of agents. Because I feel like, okay, great, you have large language models that can process internet knowledge, but mostly in natural language. But then in science, especially physical science, we don't do things just by reading papers. We actually run a lot of these physics-based simulations to understand the impact of experimental design, the mathematical models, right? So can we combine the best of two worlds together here? And naturally, the framework is that we can treat these simulations and emulators that we have built as external tools for LLM agents. And we can leverage the fact that these LLMs are very good with informal reasoning, and perhaps they can utilize the tool and complete the feedback loop for hypothesis generation to experimental design. But then if you think about the common agentic framework, like using tools to browse a website, the tools in physical science are quite special in the sense that, one, they're very expensive to use, right? I mentioned examples of climate. You have to wait for 6 months to get the feedback from the climate simulator, even though you can use our emulator to get those response in 1 week. But still, that's a scalar signal that you can get only after 1 week of wait time. So we have to be very sensitive about the cost of running these tools and when to run these tools. The other thing I think is special about physical science is that there's a lot of these formal mathematical models and programming language available to sanity check the validity of the predictions. So unlike social science, physical sciences have a lot of principles that we can leverage, whether it's laws of physics or formal languages like Lean, right? Can we leverage the power of these formal reasoning tools to improve our agents is our next question. Of course, there is also extreme uncertainty, both from the tool itself and also from how the agent reason and act in this tool environment, and how to couple this kind of uncertainty together to inform better reasoning is another challenge. So, okay, I'll give some examples of how we think about agentic AI for physical sciences, and hopefully that can bring up some more discussions about how you guys think about this problem, and perhaps we can do some mutual learning in this field. One of them is about expensive tool use. This is a paper published last year, actually early this year at ICML. The idea is that we want to use tools, but only when necessary, because these tools are quite expensive, so we don't want to become over-reliant on tools. And here the tools refer to a large range of physical-based simulators. So we want the model to adapt based on the question difficulty, and therefore we have this kind of adaptive paradigm for the agent to decide how they were going to solve the task. But the first question arises is, how do we interface the large language model, which is often reasoning in natural language, with a numerical physics-based simulator? So that's how we use these templated approaches to interface with scientific simulations. So for example, if we want the large language model to solve a climate-related question without physics-based simulators, then we can take out the parameters of the simulator, treat them as domain-specific language, and then pass the parameters to the language model. For example, we can say, how much will the temperature in a particular location under certain scenario blank change if the emission pattern is decreased by a certain amount, and blank, right? So these blanks are filled in with input to numerical simulators. Of course, like the downside of this type of templated approaches is that you are limited to the type of parameters that the numerical simulator can handle. So if you ask a free-form question that is not within the domain of the simulators, then the model will have a hard time to understand and answer the tools. But then you will have to rely on its own internal knowledge to answer the tool, which can very easily subject to hallucination. You can also ask model more open-ended questions. Say if in epidemiology, you are tasked with managing California's response during pandemic. So given certain scenario blank and some initial condition blank, we will ask model to design certain policy in California that will minimize the number of deaths. So that framework, adapting while learning, or AWL, is actually a two-stage approach. The first stage is fine-tuning. So we're trying to teach the model how to use these simulators by generating a lot of these paired question and answer data using our templated approach. So then the model is fine-tuned to internalize the knowledge of the simulator, which we call the word knowledge learning. And the second stage is tool usage adaptation. So that means we want the model to judge the difficulty of the question, and then based on the difficulty of the question, to decide whether they're going to use the tool or not. So as you can see, the type of effect of this two-stage approach is that once you fine-tune the model with simulator programming traces, then what used to be hard question now become easy, right? So the red and blue indicate the difficulty of the question. So blue is easy problem, red is hard problems. So once you have word knowledge learning, the easy problems expand, but hard problem shrinks. And with tool usage adaptation, so the one with the hammer means use tools, and then without is do not use tools. So for hard questions, we want the model to use tools. But for easy questions, because it's expensive to use tools, so we want the model to not to use tools if possible, but rather in relying on its own internal knowledge. So we run this benchmark with some of the frontier models and show that this type of adaptive approach does improve upon the frontier models, including GPT-4 and Cloud 3.5, across a wide set of physics-based tasks. What's special here is tool use is actually just forcing the model to use tools all the time. And our base model is a Llama 8B model. So it's a very small model compared to those frontier model. And despite the fact that tool use cost more than adaptive approach, it actually performance is not better because these models become over-reliant on tool using and therefore have a hard time generalize to new problems. So right now we're extending this framework to handle more complex questions and interface with a larger range of physics-based simulators, and we're also open to collaboration. The next phase is how do we bridge these formal tools in physics and math with informal reasoning of LLMs. So this is actually a quite new paper to appear at NeurIPS. Yeah, for math workshops, it was selected as a contribute talk of Spotlight. As a result of an internship of my student at Apple. So the overall problem is trying to solve mathematical theorem prover. So we want to prove math theorems. And as you know, we have these informal reasoning model that are very good with solving mathematical proofs. In fact, Gemini actually officially achieved the gold medal standard at the International Mathematical Olympiad. The challenge, however, is that these informal reasoning models, they generate proofs in natural language. So to verify the correctness of these proofs, a human expert would have you read the proof line by line. It's very time intensive, and there's no guarantee that this process is error prone. And another challenge is these informal models are still prone to hallucination. So they can generate proof that sound correct but may not be correct. And in programming languages, there are a set of tools based on formal languages like Lean, Isabella, and Rock. So thanks to these formal tools, there's also a different family of LLMs called prover LLMs that are specially trained to generate formal programs. So there's famous ones like DeepSeek Prover or Gödel Prover. They generate formal programs, then that can be programmatically verified automatically. So they don't hallucinate and you can easily check the correctness of the proofs. But the challenge here is that informal reasoning models have much, much better performances in theorem proving than prover LLMs, but then they're prone to hallucination. So how can we bridge the gap? So in this paper, we think about, can we combine informal reasoning and formal theorem proving abilities together so we can fill this gap? And the idea is that maybe we can first draft an informal proof with informal reasoning LLMs. And that's basically what you see here in this diagram. So you have a statement in natural language. We use informal reasoner to generate this type of informal proof. And then for each of the informal proof, we can generate a formal sketch, right? And that's a process of auto-formalization. And then this formal proof is already quite similar to what Ling would generate. Then you would use these off-the-shelf prover LLMs to generate the actual program in formal language. And each of these formal programs can be verified automatically with Ling and other solvers. So that's the idea. And then we proposed Hilbert, which is a recursive framework to combine informal reasoning with formal math. So the idea is if you have a target theorem, you will run a prover to solve it. Then if it fails, it will proceed with this step called sub-goal decomposition. So the idea is that we will decompose a complex theorem into a set of sub-theorems, each of them slightly easier than the original theorem. And then for each of the sub-goals, we will run the prover again to solve it. And if it fails, we will do a shallow solve and then go back to sub-goal decomposition again. And we repeat this procedure recursively until we solve all the sub-goals in this target theorem. So the key step in this algorithm, Hilbert, is sub-goal decomposition. And I will elaborate here about this step. So sub-goal decomposition is trying to decompose a complex problem into a subset of easier problems. So suppose you have a target theorem, we will use a retriever, which is an informal LLM, to retrieve a lot of useful theorems. So this step is very similar to retriever augmented generation, but instead of vector embedding, we directly retrieve lemmas from library. Then we combine these lemmas with an informal reasoner to draw a proof sketch. Then for the proof sketch, we can easily verify whether the proof sketch is correct or wrong, right? Then we go back if it's incorrect. So then we can use each of the proof sketch to further reason about each of the sub-goals. Essentially, like what are the sub-theorems that we can prove to reduce the complexity of the problem. Then we run the verifiers again to check each of the sub-goal. Once they're verified, we will run this informal reasoner to assemble all the proofs. So essentially, the part that we use is to combine the informal LLM as the reasoner and with the verifier using Ling. So we also use this informal reasoner to assemble the proofs from prover LLM. And finally, we can complete the proof. This method is now the state-of-the-art method for theorem proving. This is a benchmark from Mini F2F, which is a benchmark for mathematical theorem proving on the left. And then on the right is the Putnam bench, which is one of the most difficult theorem proving benchmark out there for formal math reasoning. So Hilbert is actually ranked #1 among all the solutions out there. And the blue here is highlighted our method. And we just want to highlight the delta that we have achieved compared to the base model. Note that there is no fine-tuning involved. Everything is inference time optimization, right? The trick is just to combine informal reasoning LLM with formal prover LLMs together. So we compared, for example, Hilbert with the base model Gödel prover. Gödel prover originally only for Mini F2F on the left. Gödel prover originally only have 70-something% accuracy, but once you have this sub-goal decomposition step, we can improve the performance by 20 points. And this kind of improvement is more pronounced in Putnam bench. As you can see, Gödel prover V2, which is the best formal LLM prover out there, for Putnam bench, it was only able to solve 1% of the problem. Putnam bench is this high school level math Olympia competition problems. So they're very difficult to solve. And Gödel prover can only solve 1% of the problem. But just by combining Gödel prover with a Gemini model, we can solve 70% of the problem. So now it's #1 in the leaderboard for the solution. That shows you the power of combining informal reasoning with formal provers. Note that now these proofs are completely in formal language, so there's no hallucination, and it can be verified automatically with verifiers. Finally, I want to talk about this new project that we have been working on for the past 1.5 years, supported by DAPA. And the idea is to build an AI co-scientist for climate science. The project is called Genie, where the idea is we wanted to combine very rich numerical data in climate science and weather science with rich text data, including climate reports, news articles, research papers. If we build a foundation model, then we can fine-tune that for a variety of tasks, such as forecasting, causal inference, and scenario creation. What's important here is that we need to ground these foundation models with unique principles in climate science, such as laws of physics, the prediction uncertainty, and in-context learning. Recently, we put out this paper called Zephyrus, an agentic framework for weather science, and it's going to appear at Europe's 2024-5 workshop on scaling environment for agents. This is a very large collaboration with faculties in computer science at UCSD and the climate scientists from SIO. And we proposed this Zephyrus agent. So given a query, for example, presented below the data set is a global weather field. Based on the data, please enter the following question. Ascertain if an extreme weather event is present, occurring within a given time frame and such a location, and please specify the affected country and its region for this extreme event. So this is a quite complex weather-related question. Then this agent will write a code block, which is then sent to a code execution server. The server orchestrates several tools unique to weather science to execute the code block, and then return the execution results back to the agent. Then the agent either decides to execute more tools or to refine its output or respond back to the user. So we'll have two major contributions for this paper. One is this agentic environment that we have constructed, which is the Zephyrus world. This world has very parallel, efficient code execution server. And the code execution server orchestrates a variety of tools, including numerical weather data, WeatherBench 2, the global climate modeling simulator, the one that we have built, and also in collaboration with Google, we have a JAX-based global climate simulator. We have a geolocator that can map natural language description of a location to precise longitude and latitude coordinates on the map. And then we can orchestrate these tools in parallel with this scalable design of code execution server. The other contribution is a benchmark for agents. So in this case, we created the semi-synthetic tasks for the agent. So for weather science, there are about 31 tasks that we created with a variety of difficulty levels, from easy questions like, say, what is the temperature like in San Diego, to hard questions like figuring out an optimum policy to reduce fire risk. So there's 31 different tasks in this agentic environment. The way we created this benchmark task is essentially extract claims from weather text corpus, and then use an LLM to generate reusable question templates. So these templates are verified by human experts in climate science. And based on the template, we will ask a coding agent to generate a code for each of the template questions. And we will then synthesize the reusable templates, the data set together to generate synthetic past data. We did an initial benchmark for the off-the-shelf models with and without agentic environment. So text-only LLM in green is just the off-the-shelf LLM presented with the questions. So of course, they're not doing very well because they don't have access to this agentic environment and the set of tools. But if you give them in the environment and set of tools, then we can see with two different type of workflows, reflective and direct answer, we can improve the performance roughly by 20 to 30%. But still, this benchmark is very challenging. Even with all the tools available, the agents can only perform 50% accuracy for all the tasks that we have presented. Finally, let me show you a quick demo of this agent in action. So basically, this is a very easy user interface where a climate scientist or a policymaker can come in and just ask a question. And the model will, orchestrate a lot of tools in the backend to interact with rich spatial temporal data in climate science. So for instance, you can ask the model a question about plot a linear regression of average temperature in Japan in 1970 and 2020. And the model will generate a code block to produce a visualization plot and a natural language response, both of which can be used to aid scientific analysis. You can also examine the code base generated by the agent, right, to check whether the answers are correct or not. You can select a region on the globe on the left and then say, please provide a meteorological report for this condition in this region. Then the model will generate a detailed human readable report for the weather retention specific to the selected region. And we can also call the forecaster tool to compare the forecast with the ground truth. So the forecast tool is actually developed by UCLA faculty, a DTS group. We actually use Stormer as our forecaster tool. Then the model generates a 7-day forecast in natural language and compare that with the actual wind speed. You can also use the Genie for anomaly and wind speed detection, and also ask what-if questions. As you can see here, each of these tasks before in climate and weather science, we would have to build a different model for each of the tasks in the past. Now, with the rise of foundation model, especially agentic foundation model, we just have a single user interface and a single foundation model in the backend that can support all these questions in a single shot. So that shows the promise of the idea of foundation model, and hopefully we can continue improve this model and can complete a lot more challenging tasks. So just to conclude, I have showed you some examples from our group, and a lot of them are just work in progress of how we work at the intersection between AI and science. And I truly believe that science represents an exciting frontier for AI, and AI represents the most accelerating new instruments in the hands of scientists. So we do imagine a future where scientists and engineers work together with AI agents side by side, from hypothesis generation to experimental design to data analysis, and the entire feedback loop to our scientific discovery. AI will co-pilot with scientists at every stage of this process, and scientists will provide the necessary guidance to ensure AI is conforming to the scientific truth. Okay, so that basically concludes my talk. You can find the code and data set of the content I described on my website, or follow me on social media. And I also would like to thank the funding agencies for supporting this work. Thank you. I think we have about 18 minutes for questions. Okay.
I want to say thank you, Rose, for today's talk. I actually have one question about
Sure.
the second part of your talk, because I
Do you
also
want to also record the question answers, or?
I'm fine with that. If everyone is okay with that, I'll keep recording. Or okay, fine.
But I'm just worried that people might be shy.
Yeah,
with
let me just
asking
stop
questions.
recording. I think that's the past practice.